optimal as well, then you could use this one. We basically use breadth first search with depths to avoid the infinite loops. Exactly. That's kind of, so it is a depth first search, but because of the I'm sorry, the like the borders we have, we do indeed avoid the infinite loops. Yes. Step 3, of course, if it is the goal node, we stop and else go to step 2 until we find our goal. Okay. So the last one is depth limited search. Here you don't really need to know the order. Honestly, it's just kind of like depth first iterative deepening, but you just have one limit, right? So it is just like depth first search. It's a LIFO stack. You could see it as depth first iterative deepening, but it just explores up to one set depth. So it doesn't go depth 0, depth 1, depth 2, depth 3. If I just say I have my depth limit at 2, then I just do depth first search until that one. And if I did not find the goal, I stop. So it is not optimal for the same reasons as depth first search, as it may generate a large number of steps or a high cost to reach the goal, right? Because we didn't cut the tree up at every level, we just only have one limit. But it is complete only if the limit is higher than the depth of the goal. Does that make sense? So if the limit would be here, then it could never find the goal, right? So in order for it to be complete, it has to have this here such that the limit is bigger than the depth of the goal. Otherwise, it cannot reach it. Does that make sense? So if the limit is underneath the goal, we can find it. And if the limit is smaller than the depth of the goal, so right here, then it will not find it. It is not optimal since it's just like depth first search. So it's a finite tree, and depth first search is also not optimal because it can take a long time to get to the goal node. So even though there's a limit, it could still be a very deep tree, right? So then it could generate a large number of steps or a high cost to reach the goal node. So that's why it's not optimal. And it's only complete if it adheres to this. Okay. So this is from the slides as well. This is kind of an overview of what we just talked about. So is it complete? Is it optimal? Yes or no? And then the time and space complexities as well. So as you can see here, depth limited, it is only complete if the limit is bigger than or equal to the depth where the goal is located. So this overview, I would really advise you to study as well. Okay, so let's do a little recap question. I will give you guys, oh no, let's just go through it together. So for the first one, what do the letters mean on the last slide? Yes, for this one, we could have depth, basically. So with breadth first search, you could have the time complexity depth plus 1. Sorry, with breadth first search. With depth first search, this M means the maximum depth of any node, because of course it takes as long as the maximum depth, right? Because you have to go all the way down. So, and this L is the limit, basically. So we have depth, and we have the maximum depth of any node, and we have the limit here. Okay, so let me see. Maybe Daniele, could you help me with the first one? So if we apply breadth first search, then which order would we get here for this first one? You can also answer in the chat if you like, but otherwise you can just unmute yourself, Daniele. So what does B mean from the last slide? I'm pretty sure it is the breadth. Yes, the maximum branching factor of the tree, right? So kind of the breadth. So how broad the tree is, the branching factor. Yes. Okay, so maybe David, could you help me with the first one? So if we apply breadth first search, what would be the order? Or maybe Doga? Yes, great, David. Yes. So we have A, B, C, D, E, F, G. That is correct because we go from left to right, remember? And if you would do the same with depth first search, what will we get? Yes, exactly. So if you know it, just answer in the chat. Maybe that's faster. So I see A, B, D, H, E, F, C, G. That is also indeed correct because if we perform depth first search, we go all the way down first to H, then we explore unexplored children, and then we go that way. So that is indeed the depth first search. So if we do depth first iterative deepening, does anybody know how we could write that down if we would explore each depth individually?
Then we have to, for each depth, write kind of a separate thing. So for depth 0, it would just be 1. Not just 8, sorry.
Yes.
For depth 2, it would be, for depth 1, it would be A, B, and then C.
Exactly.
And for the next one, it would be A, B, D, E, F, C, and D.
Exactly. Yes, great. Because you're basically performing the depth first search, right? But you're cutting up the tree into different depths. So we write it down like that. I also see in the chat. Yes, that is correct. Great. Okay. So the last one is depth limited search. And we say we have a depth limit of 1. So which nodes do we explore? And do we find the goal with this one? So remember, this is depth 0.
Well, I don't think we find the goal with this one.
Yes, exactly. Which nodes does it explore?
Only depth 0 and depth 1.
Yes. So ABC, right? Yes, exactly. Great. So indeed, we do not find the goal here. So remember, we had to have that limit is bigger than or equal to depth, and that is not our case here. So we say goal not found, unfortunately. Great. So those are the uninformed search algorithms, the way you apply them, if they're optimal or complete or not, and how you would go about a question. So usually you could have questions about data-driven or goal-driven. What is the goal? What is the search algorithm I have to apply in order to find the goal the fastest, right? That could also be a question, or anything like that. So make sure you understand these, and I feel like you guys already got the hang of them, so that is great. Okay, now we finish uninformed search. Let's have a 15-minute break. Okay, so let's do until 10:30. I'll just write it down here. Break until 10:30. And then we will move on with uninformed search. Okay? So I will stay here during the break. If you have any questions, please let me know. And otherwise, I'll see you in 30 minutes. Yes, so I've got a question. Will the slides be shared after? Yes, if you join the WhatsApp group, maybe during the break, I can just go back to the QR code real quick. This one, I will share the slides afterwards with my notes on it and everything. So you will get those. Yeah, I can see if today, if I can like share them up until the point that we discussed today. And then tomorrow you will get like the full thing. Yes. Yeah, so I think 19 or 20 of you are already in the chat. I think almost everyone is in there. If you did not join yet, then please join so you get the slides as well. Yes, so I would say goal-driven is when there are very large branches, right? So because if you have very large branches and the goal is all the way down here, then it would take you a long time to like go through everything until you find it. So then goal-driven would be easier if you have long branches. Large branches, let's say. So if the branching factor is very high, so this goes like all the way across, then it takes you a very long time to like go through it and find the goal, right? So then it's easier to do goal-driven. For this one, it's usually just when there are a lot of goal states. Then you can do a data-driven one, because then you are sure that the first one you encounter is the one that is closest to you. Okay, great. So these are the nodes for this one when there are a lot of goal states, and these are the nodes for this one. No, I just want to. Yeah. Okay, so the break is over. Let's move on with informed search now. Okay, so we just talked about uninformed search. Now we're going to talk about informed search. So uninformed search is a searching technique that has no additional information about the distance from the current state to the goal. So the one main difference between informed and uninformed search is the use of heuristics. So informed search is a technique that has additional information about the estimate distance from the current state to the goal. And it uses this knowledge to find the most optimal steps towards our solution. So that is the main difference here. So let's see a very easy example. What are heuristics exactly? So a heuristic is a function that ranks each step based on the available information to decide which path to follow. So here we see a mouse that is inside of a maze and it wants to find the cheese, right? And in our case here, the heuristic could be the smell of the cheese, because the stronger the smell of the cheese, that means that the mouse will have information about where the cheese is located, right? And then it will be able to find the optimal path to the cheese faster. So it will probably not explore this way, but because it is using heuristics, it knows that it has to go somewhere in this direction. So we could write this down as a graph, which is kind of a funny looking graph like this. So this is our goal state, this is our initial state. And because of this heuristic of the smell of the cheese, basically, it is able to find it. So if we would write it down correctly, at each edge, we can basically write down the distance. So what is the distance from this one to that one? What is the distance from this one to that one, etc. And we can write down the heuristic value. So that would be the smell or the estimated distance to the cheese. So if you're at the cheese, then the heuristic is 0. That's where you want to go. So the distance to the cheese is 0. And at your initial state, you're at heuristic value 90. So you basically want to follow the path that has a decreasing value, right? Because the more it decreases, the more likely you are to come to the goal. So at this first state here, we could have the chance to go to the node with value 85 or the node with value 100. So which one would it choose in our case? Would it go up or would it go to the left? Yes, up, exactly. So if it would go up, then it would reach this lower heuristic value, right? So we would do that for the entire graph. And that way, in the end, you will reach 0, which is where the cheese is located, and thus where the heuristic value is 0. So does that make sense? It's kind of a fun example in order to remember what are heuristics exactly. So it's just information you have about the distance to the goal. Okay, so indeed it will go up. Where do the weights of the edges come from? So in our case, that is kind of the distance. So this is also usually given information, because otherwise you wouldn't like, the whole thing about informed search is that it has additional information, right? So here we could say this edge to this edge is 8 steps for the mouse, for example. This is 3 steps. So in the end, you know, like the entire distance, and because you're using heuristics, that way you kind of make sure that you're choosing the shortest path. Yes. So in the end, by using the heuristics, and you would add up all of these values, you would get a shorter distance value, right? Than if you would just go around anywhere, try to find it, go back, then the distance would be much larger. So that's why you're using heuristics, in order to like find hopefully the shortest path. Okay, and how do we calculate this heuristic value? We usually have this formula here, which is used for A search and A star search as well. So Fn stands for the estimated cost of the cheapest solution, right? So just the estimated cost to the goal that we want to know for a certain node. And we calculate this by adding up these two values, which is the cost to reach the current node from where we are right now to the start, plus the cost to reach current node n from the goal. And if we add these two up, we have a rough estimation of, in our case, let's say the smell of the cheese or anything like that. So that is our formula that we use. Okay, so which algorithms are informed search algorithms? In our case, we need to know these 3 or 4 actually. We have hill climbing, greedy best first search, and then we have A and A star search. So let's look at hill climbing first. So for hill climbing, I have a little step guide. So you start with the initial node, and then you go to the next step based on the heuristic value. So hill climbing is a greedy search algorithm, meaning it is literally greedy, right? So if it sees it is at value 10, and here it sees value 8 and 5, and you want to have the smallest heuristic value possible, then it is greedy, so it goes to the smallest one. And that continues on in the tree. So it follows the path, whichever one has the smallest heuristic value. In the end, if there's no better step or the goal node is reached, then you stop, and else you go to step 2. The important difference between hill climbing and greedy best first search is that hill climbing does not have a memory. So if here you find out that you only have 11 and 15, and you know actually that 8 is a better value, you cannot go back, because it does not store a memory, right? It only looks at the nodes that are in front of itself. So it cannot go back. So that's kind of the downside of hill climbing. Was there a question? Okay. So then we have greedy best first search, which I always like to look at as like it's smarter older brother kind of. So we start with the initial node as well, and we go to the next step based on the evaluation function, so based on the heuristic value. But the key difference here is that it keeps nodes in memory. So like we just had that, if you go all the way down and you find that this value is actually better than this one below, then greedy best first search can go back and then visit that one. So that's kind of the optimal thing about greedy best first search. It can go back. So this is the main difference you need to know between hill climbing and greedy best first search. So what does this mean for hill climbing? It means that sometimes it will not find the goal, right? Because it can get stuck down here whilst the goal is maybe here, but it cannot go back. Okay, let's do a little recap question. So let's try it ourselves. So we have the goal node I, and we know that the lower the heuristic value, the better. So if we perform hill climbing on this search tree, what do we find? let's see, maybe Elaine. Sorry if I mispronounced your name. Elaine Jans? Jans? Could you maybe tell me what hill climbing would do in this situation? It will go to B first. Yes, exactly. So it will first visit B from A, and then where will it go? And then to E. Okay. Let's see. In our case, we want to find the lowest possible value, right? So if it goes from A to B, we go from 10 to 5. Will it then go to a value that's higher than 5? Yes, exactly. Good. So it will not, right? Because we want to find the smaller values. So if we go from 10 to 5, that is correct. And then it will just stop. Because hill climbing does not have a memory, right? So it cannot know that, oh, yeah, I'll just go back to C, right? It cannot do that. So the order of the letters that will be visited are just A and B. And then the algorithm will terminate, so it will not find the goal. So that is hill climbing. And if you would do greedy best first search, do you have any idea what then would happen? So I kind of gave it away. So after B, where would greedy best first search go? C, exactly. It will go to C, right? Because it is the same value, so that doesn't matter. It needs to find the same value or something smaller. And then after C, G, good. And now it has not found the goal yet, right? Because we have not found our value of 0. So what will happen now? Knowing that hill climbing has a memory. Come back to C or D. Yes, so it will actually go to D, yes. So it will not, well, it would kind of go back, I guess. But the next one it will explore is indeed D. And you might think, oh, but we're going from 5 to 6, so that could not be the case. But we're actually just going back up from A, and we're going from 10 to 6. So first we explored this one. We had nothing there. Okay, let's begin again. We explored this one. We found nothing. Okay, we begin again. And now we explore that one. So after D, where do we go to? I, exactly. And that's our goal, right? So then we say goal found. And it terminates. How will you write this down? It asks in which order are the nodes searched. So we'd say it first searched A and then B. Then we went to C and G. And then we went to D and then I. So that is the total order of the nodes that it searched. Does that make sense? Yes. Okay, great. Then that is the main thing you need to know about hill climbing and best first search. Hill climbing can kind of go back. And sorry, best first search can go back. Sorry, and hill climbing cannot. So hill climbing stops at B and it did not find the goal. And for greedy best first search, we do say goal found. Okay, are there any questions about hill climbing or best first search? All right. Then let's move on to A or A star. Oh, okay. If the goal is not in the most left side, does that mean that hill climbing will never find the solution? Well, it depends because, okay, let's say we have our tree here. And the goal is here. Then, oh yes, you're right. Because hill climbing will probably go from 10 to 5, even when it goes here to 6. We already basically forgot all about this. So when we are at A, this first one, we check what are my options. Oh, sorry, this should then be bigger. What are my options, right? once it decides, okay, I'm going down this path, it basically forgets the rest of the tree. It doesn't store it in memory, so it cannot go back to this one. So hill climbing is definitely like not complete at all, because there are a lot of cases where it will not find it. So if it does not choose to go down the right branch, then it cannot find the goal. But if the right node has a lower heuristic value, yes, good question. Oh, in that case, yeah, then it would find it on the right side. So it really just depends basically on which like part of the tree is the goal located. And if it decides to go that direction, then it will not find it. If it decides to go the direction of the goal, then it will find it. So it is optimal, but not complete. I would say so, yes, because it is indeed optimal in our case. Right, since the, let me check real quick, but it is indeed not complete because it will not find the goal sometimes, because it could go down that branch and then it will not find it. If it goes down this one, then it could find it. Let me quickly check my notes. Okay, no, sorry, it is not optimal. Because the thing is, if the goal is here, then it could still take quite a long time. Like it could go depth first, right? Because it would just follow the heuristic values. So it is only optimal when the heuristic value is admissible, which we will see in a second. But for hill climbing and greedy best first search, they are not optimal because their heuristic is not admissible, meaning that it could take like it could take a path that is not the optimal path. It could take like a back route and then come back and then maybe find the goal. Greedy best first search is complete. Complete, I believe, if in our case it could go back in memory, right? But what if we had a goal state here that is 14? Oh, but that's not really possible because if you reach the goal, then it gets to 0. I believe that would be the case, yes. Let me look that up in the break just to be sure, and then I'll let you guys know. Just to make sure I'm not saying it incorrectly, but at least they're both not optimal. Okay. Let's move on to A and A star search. So here we have another little step plan. So we start with our initial node and we go to the best next step based on the evaluation function. This one that we just saw, right, earlier. If there's no better step or the goal node is reached, then stop, and else you check the nodes again. So what is the difference between A and A star? A star uses the admissible heuristic, right? So what is admissible? The heuristic is admissible if it never overestimates the cost to reach a goal. This is very important. Oh, I'm also seeing the next slide. We will have an overview on the completeness and optimal thing. So we'll come back to that. But A star uses an admissible heuristic, meaning that it never overestimates the cost to reach the goal. And A just uses a basically an estimation of the heuristic. So we also see it here. So A uses an estimate cost to the goal, and A star uses an admissible cost. So that would be like the true cost. If it never overestimates it, then it can guarantee that it will lead us to the lowest cost path. Okay, so if we use admissible, we can guarantee the least cost path, which we cannot guarantee with A search. So to come back to the question about greedy best for search and hill climbing, so they're both not optimal and not complete. That's that's what I thought. So there could be a case sometimes that they do not find the goal and that they cannot find the optimal solution. The only difference here is that it keeps nodes in memory for greedy best for search and it does not for hill climbing. But overall, they're not very good search algorithms, as you can see here. You just have to know how they work, like what their search looks like as well. But keep in mind, they're not optimal and they're not complete. And the only difference is that this one keeps nodes in memory. And for A and A star search, it keeps nodes in memory and it is also optimal and also complete. Well, for our case, at least, the A star one is optimal. So they're both complete. A star is optimal. And A can be optimal, but not always. So I would say not optimal. And why? Again, because of the difference that A star uses an admissible heuristic, such that it will find the optimal path, right? So A star optimal, A search not optimal. Does that make sense for everyone what an admissible heuristic is and why we have this difference? I don't really understand the overestimation regarding an admissible heuristics. Are there examples of A versus A star? Yes, so in our case, if we would have something that looks like this. Let me think about it. So we have our goal. Let's say our goal is here. And A star uses the true cost to the goal, right? So we could have here we are 10 away from the goal, like 5 away from the goal. And here we are 0 away from the goal and etc. That way we know that if we use A star search, it will follow this path, right? Because it has a true cost to the goal, so it will find it. If we use A search, for example, you could just have an estimate. So what if it estimates it wrongly and it says this one is 5, but this one is 4, right? Then it could actually go into this branch and come back later to find out, oh, I actually had to go that way. But because it had a wrong estimate to the goal, it could like have a longer path or not the optimal solution. That's also why that one is not optimal. It could go this way before it then realizes, oh, wait, I'm not going in the right direction. I have to go back and actually take this one, which at first seemed like the higher cost, right? So that is why A could be not optimal and A star could be how does it estimate it? So in our case, that is usually done with information that has been given to you. So also the way that A star gets the optimal goal, right? That is because of this formula. So that's because of given information. So in our case, then it would say in the example exercise we're going to do later on, you see that A star could use the Manhattan distance, for example, and that way with that information, you can have an admissible heuristic. Otherwise, it will just give you info about, okay, let's say the amount of steps are X amount of meters or anything like that. So you need some additional information. You cannot just throw out numbers like that. Does that make sense? If we maybe do the practice question on A star, you at least know how that one will get it. And then the main difference here is that HN uses a Manhattan distance, which means we will not overestimate it. And if we would just get like given values of an estimate, then we would use those, right? But that is how they get to those values. So it is based on information you are given. Does that make more sense? So you have to look at your given information and on the way you are able to calculate this. So they just put random numbers based on whether it knows it is shorter or longer than the real values representing the real distance. Yeah, so you get like information on an estimate. So that is what A search would use. And in this example also, a star uses a Manhattan distance. So that is kind of like the shortest path you could ever possibly get. So then we know that it is not overestimating it. So it depends on the information you've been given. Okay. Let's see. So we still have some time. Let's do this recap question, okay? On a star search. So maybe Joy, would you want to help me with this one? Can you unmute yourself, or I feel like that would be easier for this one.
Yeah, I can try.
Okay, great. So we start at reading our question, right? It's quite a big one. It says we have a starting position here at D4, and we have a goal position at C1. And they want you to draw the search tree for data-driven A-star search, and it uses the Manhattan distance for our H value. So what does the Manhattan distance mean? It means that it's just an addition of the horizontal and vertical distances without taking the walls into account. So if I want to know the Manhattan distance from the start to the goal, I just go through the walls until I find my goal. And then yes, indeed, 4. So that would be the Manhattan distance there. The question is, which path will eventually be searched by A-star? Number the nodes in visiting order. Previously searched nodes with equal or higher values can be ignored. And furthermore, write down the used heuristic value of each node. Additionally, you can use alphabetical order when you encounter equal values. Okay, so that is a lot of information. Let's just try it together. So what is our starting node again?
D4.
Yes, exactly. So we start at D4. Okay. From there, let's calculate its heuristic value. So we basically take this again. So for G, we want to know the cost to reach the start. So if we are at the start, what is the cost, the distance to the start?
I don't know.
Okay, so if we are at the start, then the distance to the start is 0.
Oh, okay.
Yes, because we are already there. I'm sorry, I don't know why this pen is sometimes a bit weird. Okay. And we add that to our Manhattan distance from the current node to the goal. So remember, with Manhattan distance, we didn't need to take the walls into account. So what was the distance from the start to the goal?
4, 5.
Yes, 4 indeed, because we just take this path, right?
Yeah.
And we don't have to take the walls into account, so it is indeed 4. So we can say for D4, we start out with the heuristic value of 4. Okay, so from D4, where can we go if we look at our maze?
You can go to S4, or is it not possible?
Do you mean this one? Or?
No, the one above that.
Oh, that is where we start already. That is D4. So you read this like that, D4.
Oh, then I mean the one down, yeah, that you had first.
Yes, so that would be E4, right? That is right there. Okay, good, yes. So we can go to either E4, or we can go to?
D5.
Yes, D5, indeed. Okay, so let's calculate the heuristic values for these. So what is the heuristic value for D5? First, you want to know the cost to reach the start. So if we are here, how many steps does it take to reach our start node?
1.
Yes. And then how many steps does it take to reach our goal node? If we can
from there, it's 5, right?
Yes, exactly, because we can walk through the walls again. So then it is 5. And for E?
The same.
Yes, we have the same. Great. Okay. So if we start from 4 and we have the values 6 and 6, we basically have the same values here, right? So it says use alphabetical order. So which one would we choose out of these two?
D.
Exactly. So from D, where can we go? Oh, sorry. From D5?
You can go up or down.
Mm-hmm. So that would be C5 or E5, right?
Yeah.
Yes, C5 and E5. And what would the heuristic values be for this one?
2.
2
2
plus?
steps from the start
Mm-hmm.
and
For the goal?
4.
Yes. So we get our value of 6. And for E, we also have 2 steps from the start, but how far is it away from the goal?
6 steps, I believe.
Yes, exactly. So we do not go down that path because 8 is smaller. 6 is smaller than 8. So we continue from C5. So from C5, where can we go to?
To the left, so to C4.
Yes, there's only one option here. And what is our value?
1 step from the beginning state and 3 steps to the end goal. So that's 5, right?
Okay, so for this one, you're correct. But for GN, we cannot walk through the walls, right? So it says only for HN can we use the Manhattan distance. So if we are at C4, we actually would have to go 1, 2, 3 steps back to the start.
Oh, okay.
Yes, so take that into consideration for this one. Only HN is kind of our admissible value. Remember here, only for HN can you have like the true estimate or the true cost. So for the other one, we just want to know the path back to the start. So we have 3 plus 3 is 6. Okay. And then from C4, where can we go?
C3.
Mm-hmm.
Or you can go to B4.
Yes. Okay. So this is quite a big exercise, but we're just going to keep going. So for B4 and C3, which values do we get?
For B4 from the start node, it is 3 steps.
Okay, let's see. Before we cannot go through the walls again, right? So
Oh yeah, I keep forgetting that.
that's okay. So what will we get then?
4 steps.
Yes. 1, 2, 3, 4. And to the goal?
Also 4.
Yes. So we get 8. And for C3, we are located right there.
4 steps from the start node and 2 steps to the goal node.
Yes, great. So we see again, we have a value of 6, so we go on with C3. Oh God, what am I keep pressing buttons, I'm sorry. Oh no. Oh, yeah, okay. So from C3, do we have any other way to go?
Can you go through the wall now or not?
No, you just have to follow the path.
So you have to go up then or down.
Yes, so we can go to B3 or D3.
Yes.
And what would those values be?
5 plus 4.
5 plus 4. Let's say we're at B3. I want to go to the goal. That's 1, 2, 3 steps.
Okay.
Yes. So 5 plus 3 actually. And then for D3, what do we get?
Also 5 plus 3.
Yes. So now we've reached a point where from 6 we could go to 8 or to 8. But remember with A search also, it keeps nodes in memory. So just like best first search, we can actually go back up and then explore E4. Okay, so thank you. Let's see if someone else would like to finish it. Maybe Joanna?
Okay.
So from E4, where could we go?
From E4, we could go to either E3 or E5.
Yes. But since we already explored e5, let's go to e3. It also says here, previously searched nodes can be ignored. Why is d3 5 plus 3? Okay, so let's go through this question. D3, right? So we want the cost to the start. So
E3? Or
that is, if we go back, that would be 1, 2, 3, 4, 5, and then to the goal that is 1, 2, 3. So you have to like go to back to the way you started. So you cannot just say, okay, the distance from the start is 3. Maybe that's what you were thinking. You have to go back the way you came. Yes, okay. So I just answered the chat. Yeah, so that's 5 plus 3. Okay, sorry, Joanna. Let's go on with E3. What did you think the value was?
so 2 plus 5, I think.
2 plus 5. Let's see, we're at E3. That is indeed 2.
Oh no, 4.
Yes,
It's 4.
4, exactly. 1, 2, 3, 4. So we're at 6. Great. Okay, so from E3, where can we go? Right now we're here.
We can go to either D3 or E2 from E3.
Yes, so we can go to D3 or we can go to E2. Exactly. So what are the values for those two nodes?
For D3, it's 3 plus 3.
Mm-hmm.
And for E3, it's again 3 plus 3.
Yes. So which one do we pick here?
Alphabetical. So D2.
Yes, exactly. So after D3, where do we go?
We could go to either D2 or C3, but we've already been to C3.
Great, yes. So what is the value for D2?
4 plus 2.
Mm-hmm. And then where do we go? We also only have one option.
To D1.
Yes. And what is our value there?
5 plus 1.
Yes, so we go to 6 again, so we can move on to our final node, which is
C1.
Yes, so that is our goal, right? But let's just calculate the heuristic value to make sure we're there.
6 plus 0.
Yes, 6 plus 0 is 6. Great. That is correct. Thank you very much. So if we look at the path we just followed, we went from D4 to D5. Then from here we explored, okay, we can either go to 6 or 8. So we choose 6. We go down like that. We chose C3. And then from here we thought, oh, okay, we either can choose between 8, 8, or the 6 that was stored in memory. So then we go to 6, right? We have 6, 7. Then we chose alphabetically 8, 9, 10, 11. So this is the total order of the nodes we visited. And now the final question is, which path will be eventually searched by A? Okay, I got a little question. Why is there D3 2 times? D3 2 times.
Yeah, it's under C3 as well.
Oh, yeah. Yeah, it was previously searched. You're right. But from the path we're taking right now, we're taking another path. So then in our case, the heuristic value would change. So if we would take from E4, let's see, E4, you could argue that you could also go to E5 again, right? If you calculate this heuristic value, what do we get? Oh, you get it. Okay, great. Yes, because that would be bigger again. What is the difference between greedy best first search and A or A star search? Okay, so for greedy best first search, it is not optimal and also not complete because it's not using this heuristic formula. Basically, for greedy best first search, we only use our heuristic value, which could be the estimate distance, right? So it's also not admissible. So in our case, it just greedy best first search just goes through the steps, chooses the one that is best, and then it can go back. But it does not use the admissible heuristic, or it does not use the formula we just used. So that's why it is neither optimal nor complete. But with A and A star, we are sure that it is complete. Would we ever get a question like this on the exam to draw the tree? No, you would not have to like draw the tree as an answer. But if the question here, which we still have to answer, which path will eventually be searched by A star? Does anyone know what the answer would be to this? So we explored a lot of nodes, but what is the eventual path that we take in the end from the start to the goal? So do we even go back into this left branch, or do we just immediately return this path? The right side, indeed. So our final answer is yes. Great, Anna, indeed. We start from D4, then we go to E4, D3, D2, D1, and C1. Yes, so that is the path. That is indeed correct. So your a question on the exam wouldn't be like draw the tree, but the question could be what is the path? Then still it's a multiple choice, right? So one of the options would be this, and then that is your final answer. Does that answer your question, Ruvantika? So you will, for yourself, you will have to draw the tree in order to find the answer. But the thing you will actually have to answer is this one. Okay, great. So that was a long one, but it's very important you understand how to calculate these things for A and A star search. Isn't E3 in the path? Oh, sorry. Yes, I skipped it. Great. D3 as well, though, but we are going from E4. Sorry, E3 as well. So we start at D4, E4, E3. Very sharp. Thank you. Yes, I missed that one. So D4, E4, E3, D3, D2, D1, and C1. So I already prepared the answer a little bit more clearly for you. So this is indeed the final goal here. And here's our search tree again. So if you want to go back to the slide and look at how we did it there, you can try it again for yourself. And then this is the answer to the question. Okay, are there any more questions about informed search? Or do you want to see any of the other slides again?
If you could please show the slide with the table with when it shows like what is complete, what not. Thank you.
Yes. So take note of this one. All right, then let's have our break again. We just finished informed search. Afterwards, we will start with Minimax. So let's have our break until 11:30. I'm not sure if I can go back to this one, but at least, okay, we finished it. So let's have a break. Until 11:30 again. So a bit longer than a 15-minute break. And again, if you have any questions, you can ask it in the chat or just unmute yourself. I'm gonna get something to drink and then I'll be back in a few minutes and then you can ask me questions during the break. On the slide about the difference between the uninformed searches, why are there asterisks next to the breadth first search? I think that's another, or is that the one from the slides maybe? Because where does it have, oh, okay, but does it have it next to optimal or next to complete? I would maybe say next to optimal. Okay, so for optimal, it kind of has a little bit of a like a conditional thing there. So breadth first search is optimal if the costs of the edges are equal. But usually with uninformed search, we don't really use the weighted edges, right? But if the costs of the edges are equal, then it is optimal. Otherwise not. So maybe that is the asterisk. That is like a little bit more explanation. But in our case, we did not use that one. For complete, maybe that is also why it says that. What I knew is that breadth first search is complete. Let's see. Okay, it says here that there's one condition for the completeness. So breadth first search is always complete if the graph is finite, right? And if the graph is infinite, then breadth first search is complete under the following condition. A goal node is reachable from the start and no node has an infinite number of successors. But in our cases, with the finite one, then it is optimal and complete. But I personally did not have that in this one. Oh, sorry. Yes. So with the optimalness, it was about the costs of the edges, right, being equal. And it says here, it is complete under the following condition. A goal node is reachable from the start and no node has an infinite number of successors. So it will not get stuck in loops like depth first search does, but for a finite tree, it is complete. So if a node has infinite children or whatever, it is not complete. Yes, that's what I'm seeing here, but that's in the, it could not be complete, but that's also not always the case. So with depth first search, it can get like no goal state and it does never return because it's just in this infinite branch. But breadth first search goes from left to right. Remember? So even if there are like a lot of children, it could be the case that it just like goes on forever, I guess. So that could be one thing where it is incomplete. What condition is there for an algorithm being complete? So complete means that it will find a solution if it exists. That is complete. How does a search work again? Okay, so we have the informed search, right? Which makes use of heuristics. Okay, great. And heuristics, remember, we have something like the smell of the cheese. And the main difference between A and A star is the fact that A star uses an admissible heuristics, which means that it never overestimates the cost to reach a goal. So in our case here, we use the Manhattan distance, right, as a heuristic, which means it can never overestimate the cost to reach a goal, right? You need at least 1, 2, 3, 4 steps at least to get to the goal. But in our case, then in the real world, it has this wall here. So then it will take longer, but it never overestimates the cost, right? That is A star. So its H value is a true cost to the goal. You can always guarantee to find the least cost path when you have an admissible heuristic. And with a search, all the information you're getting is only an estimate to the goal. So then you could have that it follows a path. Like I said here, it could follow this one because it says, oh, 4 is smaller and 7 is smaller. Oh, but then I have to go back because the goal is actually here. But if it was an admissible heuristic, then that would not happen, because then we would have the true cost to the goal. So then it would not explore this one. It would just go straight to the left branch where it will find the goal. So then it will only go that way. Yes, okay, great. So that's the main difference, the admissible one. So that is also why here they both keep nodes in memory and they are complete, because if there's a solution, they will find it. But only A star is optimal because it uses the admissible heuristic, such that here, as we saw, it finds the optimal path, right? Because it goes straight to it. And if it was not, if it was like that for A star, then first it would go there, then it could take like a back road loop back. So that has, maybe not in this exact example, but A star could have the characteristic that it could not be optimal. Yeah, so this one is quite an important slide. Okay. So yeah, I would really advise you to know like the characteristics of them and also how they work in search. So for hill climbing or best for search, you could get a question like this, like which path does it follow? And then you need to know the step guide, remember, how does it work? Does it keep nodes in memory, yes or no? And then for A and A star, this is also very important. It could ask like which algorithm is optimal. Then in our case, we would only answer A star and breadth first and depth first iterative deepening, right? So if I would have like an overview of, let's just do it here, which search algorithms are optimal. Then you have to know the 3, which are breadth first search and depth first iterative deepening, right? Because since there are limits, we guarantee that it is optimal. And 3, we have A star. Let's go back here. You see iterative deepening is optimal, breadth first is optimal. These 2 are not. And for these, we have that only A star is optimal. So if the question is which algorithms are optimal, it's these 3. So I got a question. Do we need to know the time and space complexity? So if we go back to the table, you don't have to know like the exact values here. Like you don't have to memorize them. You just have to know like which one is faster, which one is not faster, and why. For me, it makes more sense, right? That, for example, depth iterative deepening takes longer than the other one. Also regarding time, right? Because it has to go through it and through it again. So you don't have to like memorize the values here, but you do have to know just like which one is faster, which one saves more time or space, things like that. So you know that depth first takes a long time, right? And you know that breadth first is faster. You know that depth first iterative deepening has a larger time and space complexity, but at least it is optimal, just things like that. So you have to know the general idea, but they're not going to ask like, what is the exponent here? Like I've never seen anything like that. So does that make sense? You just have to like understand the general structure of them, definitely, but not the, I never memorized like the actual values and everything. Okay, great. So you could have like a question like true or false, or which one is correct, saying things about the time and space when they are comparing them. So just compare them for yourself as well, see if you understand the differences, and that way you should be able to answer those questions. So like a lot of the practice examples that we're going through now are either just practice questions or questions from the work group, right? Just to see if you understand the theory. And then the exam questions will be new questions, and that really determines like how you would do at the exam, right? Because they show the structure you get there. They will all be multiple choice. They will be questions from practice exams, stuff like that. Okay, so we can almost start again. Our last topic for today is Minimax with alphabetical pruning as well. So can we start? Yes, we can start. Okay. So remember from informed search, you need to know how does this work? What are heuristics? What formula do A and A star use? What is admissible? That is very important. Are they optimal or complete? Yes or no? And then how you would draw a search tree for A star in order to answer the question. So those are the main takeaways, I'd say. And if you have a question about which ones are optimal, just remember these three. Okay, so for the Minimax algorithm, let's start. So the Minimax algorithm usually is a representation for games. So you could have a two-player game where, for example, Min and Max always play optimal, where Min chooses the lowest value and Max chooses the highest value. This is usually represented as a tree. So this is a little example here. We have tic-tac-toe, right? And then you can represent this as a tree with Min and Max, a two-player game, etc. So a little step guide for the Minimax algorithm is that you start at the lowest depth without any values. So here you can have like 1, 2, 4, 5, etc. And you determine the max or the min value for that child node. So basically, for this one, you choose either between 1 or 2. If it is min, you choose 1. If it is between 4 and 5, you choose 4, etc. So if the root node is determined, so you work your way up. Once the root node is determined, you stop. I feel like this should be parent, actually. Oh, from the child node. Oh yeah, sorry. From the child node, you determine the value for the parent node. And then once you reach the root node, the final value is determined, and then you stop. So if this final value would be, for example, 3, and the rules of the game state that if you have less than 5 points, you win, then min wins. If the game was that you have to have more than 5 points, then max would win, for example. So that really depends on the rules of the game. So it could be represented like this, where max has different symbols than min, like circles and squares. Usually it is given on the side. And if it is not, then it's usually stated in the question, for example, min makes the first move. So then you would choose the value for min first, for example. Okay, so let's do a little recap question here. So they want you to consider the following tree and using the minimax algorithm to compute what the heuristic value is at each position. For max when both players play optimally. So max always chooses the highest value and min always chooses the smallest value. We can assume that max makes the first move. So then in our case, max is here, right? It makes the first move. Then for the move afterwards, it's min's turn. And then finally, it is max's turn. So let me check. Maybe Kevin? Do you know what I have to fill in for this tree? With the minimax algorithm?
Yeah, so for the the second level, for the second level, right, the C's, there you pick the highest one from the children. So for C1, that would be 5.
Mm-hmm. And then just
yeah,
just
then continue.
Then what will we get?
11.
Mm-hmm.
And 8, 4, 12, 2, 3, 11, and 5.
Yes, exactly. And then if we would go then to min,
then you would pick the lowest value from the children from the B, and so that would be 5, then 2, and then 3.
Yes. And then max would pick
The highest of those 3, so 5.
Yes, exactly. Oh, yes, great, thank you. So that is indeed how minimax works. So you see whose turn it is, and if they play optimally, then min chooses the smallest value from all its children, and max chooses the highest value. So that was perfect, yes. Okay, so then we have something called alpha-beta pruning. So what is alpha-beta pruning? It is basically a minimax application where we prune, which means basically like to ignore, I guess, or like cut away. Oh, am I right? Ignore? Yes, sorry. Unnecessary nodes. And this lowers the time and space complexity, right? Because then if it prunes the nodes that are not needed, then it can go through the tree faster afterwards. Okay, so I think it's easiest if I just go through this recap question and then afterwards we try one ourselves. Okay, so we consider the following search tree that contains heuristic values at the leaves, and the player on the move is depicted at each level. So we start with max, then min, and then max in the end. Again, the goal for min is to have the smallest value and for max to have the largest value. So the question is which nodes can be ignored if we apply alpha-beta pruning. So let's go through this one together, and then afterwards we have another question where we can see if you understood it. Okay. So we have to start out at this left-hand side of the tree, right? And we know that max is at play. So one value that we know for sure is that max will choose 4 at this node. Okay? Then what happens? We know that for the next layer in our tree, that it is min's turn. So min now has the choice between a value of 4, which has been given, or something smaller. So like minus infinity, anything that is smaller than 4. So for each step, you write down which info have I obtained at this step and how does it affect the outcome of the game. So after we know that, we move on. We check our next branch. We check this value of 6. We know that for max, right, for this node, we can choose either 6 or anything that is bigger than 6, right? We have not looked at this yet. We know that we have 6 or anything that is bigger than 6. Now the question is, do we have to look at this node or not in order to do the alpha beta pruning? Who thinks we can prune this node and who thinks we shouldn't? Okay, so I think no, we don't have to look at it, right? Is that what you mean? Or no, we don't have to prune it? Exactly, prune. Yeah, I think that's what the others meant as well. So indeed we can prune it. And why is that? Because if we look here, we already had our value of 6, right? What I always ask myself is, does it matter for the outcome if the node has a smaller value or a bigger value? And if the answer is no to both of those questions, we prune it. Okay, so here we have a value of 2. Or sorry, we don't know the value. We have 6 or bigger for max. So let's imagine that this would be infinity. This would be really big. Oh my god, what is happening? Okay. Then max would choose it, right? But we already know for the next layer that min will choose 4 or something smaller. So even if this value was like 5,000, it doesn't matter for the outcome because min wouldn't choose it. Similarly, if this node has a smaller value, then we already know that max will either choose 6 or something bigger. So it also doesn't matter if it is smaller. Even if this was minus 100, it will still choose 6. So for the outcome of the game, the value of this node doesn't matter. So that is why we can prune it. Okay. So for our next step, we look at, we know now that min will choose 4. That is the extra information that we've obtained right now, because we know this was 6 or bigger. So anything that comes out of this, min will not choose. So we know for a fact that min will choose 4 at this level. So always write down the info you know. What this means for the entire game means that at the end, max has a value of 4 or bigger. So that's also some information that we obtained right now. Okay, that was our first subtree. Let's move on to the next one. So we see the value of 2. We always have to check what do we have, right? Because if we do not check both of these nodes, then we don't know what we start out with. So usually, like these nodes are like never pruned because we need to know our options, right? So we start with 2. So what happens next? We know now that for the next layer, min has a value of 2 or smaller, or anything smaller than that. All right. So do we need to look at 9 here? No, prune. Okay, great. Yes, exactly. So why is that? Because if any of these values here would be bigger than 2, then min would not choose it right there, right? And if they would be smaller than 2, so even if this ended up being a smaller value, so like minus 100, we know that for the end of the game, max is at play. And max already has 4, or it needs something bigger. So even if this would be a smaller value in the end by these nodes, max would not choose it. And if it would be bigger, then min would not choose it because it already has 2 and it needs something smaller than that. So indeed, we can just prune this entire side of the tree. Yes, exactly. You have to pay attention to this one here. So it could change if it was smaller. We could have a smaller value here, but because we need 4 or something bigger, it doesn't matter for the outcome of the game, right? So that's why we can prune this entire subtree here. Does that make sense? Are there any questions so far? All right. So let's continue. So we check our final subtree here. We have a value of 5. So what do we know? We know that min at this level has 5 or something smaller, right? That's its choice. So do we need to look at this 7 value here? What do you think? No. Okay, so what would happen if 7 would be larger? There would be no change, right? Because if this is 8 or 800 even, it doesn't matter for the outcome of the game because min would not choose it. But what would happen if 7, if this would be smaller? If this would be 4? Would that affect the game in the end? Yes, exactly. Yes, so it would affect the game, because then min suddenly, we have another outcome, exactly. Because then min suddenly will choose 4 here. So then, in our case, we already have 4, but it will still affect the outcome of the game. Because if we would have 5, then Max would choose 5, right? And now, because this one is smaller, it would choose 4. So that does have an outcome on our game eventually. So in our case here, we know we have to look at this one in order to know if this outcome will change that outcome eventually. So we have 7. So we know for Max, we have 7 or something bigger. So now we look at our final node. Can we prune that one, yes or no? Yes, prune it. Exactly. And why is that? Because let's ask ourselves the same question. So let's say this was a very small value. Then Max would not choose it here, right? Because it will choose 7 or something bigger. So that doesn't matter. And if this was a very big value, let's say 800 again, Max would choose 800. But here, min would still choose 5. So that would not affect the outcome of the game, because 800 will not be chosen and it will not be affecting the outcome. So if it's smaller, then Max will not choose it. And if it's bigger here, then min will not choose it. So indeed, we can prune this final leaf node because it doesn't have an outcome on the effect of the doesn't have an effect on the outcome of the game. So then eventually we know that between min and max, min will choose 5 here, and our final outcome is 5. So this would be our final answer. We pruned all of these, this entire subtree, and this one. And because of that, now Minimax has a lower search time, because after the pruning, it starts to search and it can just ignore all of those. And then you lower the time and space complexity in order to find your final value, basically. So my advice for this one would be, just for every step you take, write down what information do I have. So even at this one, here you start to know, okay, so for my final outcome, I know that Max will have 4 or something bigger, right? Just write everything down such that when you arrive at this part of the game, you know that these values will not influence this outcome, such that you can prune this entire subtree. So then this would be the final answer. Okay. So this is another one. I would advise you to try it for yourself. I think that would be the best right now. Is it okay if I give you guys 5 to 10 minutes? I'll check in after 5 minutes if you need more time. And then afterwards I'm gonna ask one of you to share your answer. Okay? I feel like that would be the most beneficial right now. Okay, great. So let's start. I'll give you guys 5 minutes. And then afterwards we can check our answer together. So just for every node you visit, think about, okay, do I need the value for this one or that one? If it is bigger, does it matter for the outcome? If it is smaller, does it matter for the outcome? If the answer is no, you can prune it. Okay, so I can just add this little hint. Um, okay. So that was 5 minutes. Do you guys need a bit more time? Or do you want to try? A little more. Okay. Maybe if you're done, just tell me in the chat. That way I can see how many people finished. Great. So I see people are finishing. And if you cannot manage, that's also okay. We'll just go through it together. Okay. Is it okay if I go through the answer with one of you guys now? Okay, so all right. 2 minutes? Okay, maybe that's fair. Let's let everyone try it. So at 11:55, I'm gonna ask one of you. Sorry. Okay. So I think we're there. Let's see. Roberto, could you help me with this one? So what did you do for this exercise?
Okay, so I basically took one from both of the left nodes,
Mm-hmm.
and then I pruned to a 9 on the second one.
This one?
Yeah.
Yeah.
I'm not sure if that's correct, but
Mhm.
And then the max would choose 1 because they're both 1.
Exactly.
Okay, for the second part, I chose 7 because that's the min one going, and I decided to prune the rest of the tree
Mhm.
because even if Max chooses a larger number, min goes next, and it wouldn't matter.
Mhm.
Also, even if the number is less than the number chosen there, Max goes next, so it wouldn't really matter anyway. Again,
Exactly. Max says like 7 or something bigger, right? So yes. Okay, and then for the final subtree? Oh,
the
why can I
last
not-
one I chose 5,
Yes.
and that's a tree, and I prune the rest again. The same logic as in the middle.
Yes. So for max, we would have up here, we would have like 5 or larger, right?
And at the end, I said it's 1.
1, exactly. Because from the left side, we had minus infinity or 1. Why is it not writing infinity or 1? Yeah. Exactly. Great. That is indeed the answer. So let's go through it with this one for the rest of the people. So indeed, we choose 1 here at first because it's Min's turn, right? And then for this next one, we check, okay, what is the other value we have? We have 1. So we know that Min can choose between minus infinity and 1. So if this,
I have a question. Is that okay?
Sure.
For the second branch, the one that you were just talking about, how do we know that it's going to take 1 if we pruned 2 and 9? one of them could have been a 0.
Yeah, okay. So the question is like, why are we pruning these two, right? So in our case, if this was smaller, let's say 0, then
Not
your
why, but how did we, like, why did we put 1 on top? How did we know that?
Okay. Yeah, so we would have first, before we do that, we would only have something that looks like this, right? Minus infinity or 1. So we have not chosen it yet, right? Because we check this first value, and in order to know what happens at this branch, we need to check what happens here. Because if this is a big value, then it will affect max. Right? So we need, why is this not working? Okay. So we need to know what happens here. Do you agree? Because if this one was 5, then max would choose it, right?
Yeah.
Okay, so we check the first leftmost node in order to get some information. So we know we have 1. So that's the one we viewed. And we know for max on this branch, it can choose either for min, because it's that one. We choose either 1 or something smaller. So here we could say if this one was smaller, then min would choose it. But we know already for the next branch that max will not choose it. And if it was bigger, then we know for this branch, min would not choose it because it wants something smaller than 1. So then in our case, it doesn't matter. So we can prune these two. And from that, we know that it will choose 1 in the end. So first you only know this. And after you've pruned these two, think here as well, right? Remember we knew we had 6 or larger. And after we went through it, after we know that that one chose 4, we know that our final value in the end was 6. So that's the same what is happening here. First, we know only that min would choose 1 or smaller. And after we know that max would choose 1 here, we can say, okay, it chose 1.
So it could be considered an assumption, not it can be something else because we pruned to a 9, which could have been a 0, but it would still, the max would still pick the 1. So for
exactly.
the one under, it could have been something else, but we can just make an assumption and say it's 1 because we pruned the others.
Yeah, it's not like, in the end, it's not really an assumption, right? Because you know for a fact that, oh yeah, it could choose something different, but it won't affect it here. So that's why we pruned them. Yes, exactly.
Okay, thank you.
Great. So for this one, I did like fill in the entire tree, so you saw the values as well, but this is actually the correct way to do it, right? So you could have some cases where it's not like determined yet. But for this one, I wanted to write down what we got here. So that would be a part of the question as well. Okay, so if we would then move on to this next subtree, we have our value of 7. So we know for this one, max would choose 7 or something higher, right? So in the end, we know after calculating this value with the 1s, right? We know that min will choose 1 or something smaller. And we have 7 or something bigger here. So indeed, as Roberto said, this thing will be pruned entirely because if this had a bigger value and we would choose 107 here, we know that for the end, min will choose 1 or smaller. So it will not choose that. So it will not look at that. So that doesn't matter. And if this was smaller, then we know that max has 7 or larger. So it will not look at that as well. So for the entire outcome of the game, we can just prune this entire part of the tree. Okay, and then for this last subtree, we check again what are our options. So we have the value of 5. So for max here, we know we have 5 or bigger, right? And which was also correctly said, we can prune this entire part. Why? Because we know in the end, min will choose 1 or smaller. So even if this value would be smaller in the end, if these values would be bigger, then min would not choose it. And if they would be smaller, then max would not choose it. So again, just always ask yourself the question, does it matter for the outcome if the value is bigger or smaller? If you say if it's bigger, then min would not choose it. If it's smaller, then max would not choose it. Then you prune it. So this is indeed the final answer. Are there any questions or uncertainties about this one? Or do you want me to go through one of them again? Or if you have a question like, why is that one pruned? Why is that one not pruned? No? Okay. Are there any questions about the other theory that we discussed today? Could be anything at all. Or any questions about the exam? Any general questions?
For the exam, do we know, because I don't remember if the lecturer said whether we would get like paper to draw the trees and everything.
Ah, right. I am getting this question a lot. I haven't double checked, but I would be pretty sure that you would get some scrap paper. Because sometimes you would have to draw this yourself, right? Or like you would have to go through the A* search tree like we did here. So that would be kind of hard to do without the paper. How many questions are there on the exam in total? Let me check, I think. Let me take a look for you. So on average, I feel like there will be around maybe 20 to 22 multiple choice questions and then one open question. But I'm not entirely sure. I can check maybe if the mock exam was kind of similar. Let me see. So there it says 27. 27, so I would around 20 to 30. And then one question is an open question and the rest is multiple choice. I would say that's kind of a rough estimation. It could differ year to year. But I would say somewhere between 20 and 25 or 20 to 27, something like that. I could ask the professor later for like, maybe he will tell you exactly, but I would take that estimate kind of. Oh yeah, the WhatsApp link. Let me see. So we still have some time left. I wasn't really sure how long this would take. So my suggestion is to go through a bit of the other theory as well today, and then move on from that. How would you suggest to study for the exam besides the sessions for today and tomorrow? Okay, that's a very good question. So, of course, the sessions for today and tomorrow. Next to that, what I personally did is I went through all the workgroup exercises again, and then saw, do I understand every single one of the questions? So basically the workgroup exercises kind of represent what you need to know for the exam. If you don't know the theory behind it, go back to the slides, go back to the book, and then study that theory up until you know how to solve every single question. From that point on, you would have to know how to answer the questions, right? You can go through the exam questions of these slides again. There will be practice exams on Canvas quizzes, and just practice as much as possible with those. I personally went from like working groups to lecture theory rather than the other way around. So that way you like know what to study, and while you're practicing, you're probably gonna find like, oh, I have a few gaps in my knowledge, and then you go back to the theory and then fill in the gaps, and you practice that way. Okay, so there's a question about the state space representation. So I believe there was only one question about that in the working groups, right? which would be, let's see what it was about. It was about like from working group 2. It was the first question, right? State space problems. So there you just had to know what is the initial state, what is a goal test, what is the successor function, and what is the cost function. Since this was just one exercise, I did not include it here, but I can send you the little cheat sheet I made for those definition points in the WhatsApp group. Does that sound good? So that is what I had on state space representation, this one. So the most important definitions there are initial state, goal test, successor function, and cost function. And then the exercise that we had, I think you guys should all have it, but I can send it anyways. Is this one. I could, if you want, I could find some extra practice. I think last year they had some more exercises on this. And then if you have any questions about it, you can tell me. So I could maybe share extra state space questions. Okay, so we still have some time left. I wasn't really sure how long this would take, so just in case I added some extra exam questions in the end, like if we would have enough time, we go through all of them. If not, you can have some for extra practice. But because we still have some time left, I would suggest going through the first theory part of logic up until like the truth tables. And then from tomorrow, we'll begin again with entailment and DPLL, and then set theory, and then the exam questions. So I hope that will fill enough time as well. Okay, so let's just go through it together. So logic and entailment. We can also do a little recap tomorrow of logic again, and then we continue. So the theory here is for propositional logic. So we have something called semantics, and we have something called syntax, right? So the semantics here are the meaning, and syntax is the expression. All right. So how do we present this in logic? So we have the syntax, which is the expression. So we have these few symbols that you really need to remember. We have the conjunction, meaning and, which could also be written like this. We have the disjunction, meaning or, which is this upside down V, or just a V, sorry. We have a negation, which could be this curly bracket. It could also look like this, or like that. That means not. We can have an implication, which is an arrow. And we have a biconditional, which is also called by implication. Okay. So what does this mean, right? We can write it down like that. So we could have our propositional variables here, A and B. So we could have A and not B, not A implies B, A or B or C. But what does this mean in the case of semantics, right? So what do we get as a meaning? So then we move on to semantics. We need to know if something is true or false in the end. And how do we know this? Again, we apply the rules, so the syntax. And we see here a table that defines the basic structure of these semantics. So we have our variables P and Q here, and they have the values true and false, and they have every single combination you could have of true and false. So let's check out the negation first. So negation means the opposite, okay? So the opposite, I believe it would say of true and false, the opposite of true or false. So in our case here, it says the negation of P, right? So if we would have true, then the negation of P for that value, true, would become false. The same here. The truth value for P would become false. Same for the other side. If it's false, it becomes true, etc. So that's what the negation means. Sorry. Then we have the conjunction, which means that all literals must be true. So it must be true and true. Only this one can yield true, right? So we have here in the table, we can see only if these two values are both true, do we get our truth value. So that's the conjunction. The rest is all false. Okay, for disjunction, we have that at least one is true. So we could have true or true. We could have true or false. Or we could have false or true, and these will all yield a truth value because we only need at least one. So they could also be both, but at least one. So let's check if that is correct. Yes, here they are both true. One is true, one is true. That is why all of these values here in the table are true, and only this one is false. All right, so that is disjunction. Then we have implication. So here you have to remember that only for true implies false do we get a false value. And the rest is all true. So for the people that attended my work group, you might already know the little trick I used to remember this, but it's really nice. So we could have these combinations, right? True and true. True implies false. False implies true. Well, that one's a bit. And false implies false. So the way that I remember what the outcome for the implication would be is as follows. This first value will indicate, did I study, yes or no? And this next value indicates, did I pass my exam, yes or no? So the way I remember the values that come from the implication is as follows. If I studied and I passed for the test, then that makes sense, right? Then I'm happy. So I get a true value. If I did not study, but I passed, then I'm like, oh, well, that's great. I'm happy. So that's a truth value. If I did not study and I did not pass, then I'm like, okay, I guess that makes sense. I did not study, so I did not pass. But the one instance where it is false is if I studied and I did not pass. Then I am very unhappy because I did my best and I did not I did not pass my test. So that's the only instance where it is false. So that's a little trick I always remember in order to know, okay, so if I have an implication and if I have true and false values, when is it false? So instead of just remembering, okay, true implies false, is it true implies false or false implies true? I don't remember. Just think of this example here. If I studied for my test and I failed, then I'm unhappy. And else I'm either happy or it's like logical, like if I studied and I didn't pass, okay, that makes sense, right? So I hope this helps. I mean, this helped me remember it for the past 3 years. So I personally really like this way of thinking about it. It's just a little trick you can use. Okay, so then by implication, it says literals have to have the same value. So in the table, we see that here P and Q have the same value, right? They're both true. And here they're both false. So only in those cases are they true. So that's what you have to know. So again, note the little light bulb in the corner. This is some theory that you have to remember in order to apply the rest of the logic. So are there any questions about any of these, any of the semantics? Or is it all clear? Okay, if it's all clear, then let's try this for ourselves. So we have a little recap question. Yes. So let's say we have a value of A is true, B is true, and C is false. I want to know A and not B. What is the value that we will get if we apply the semantics that we just learned to values A is true, and B is true, and C is false, in the case where A and not B? So what do you guys think? Do we get true or false?
False.
Yes, and why?
Because A is true, but not B also has to be true for the conjunction to be true. So
Yes.
and not B is false in this case.
Exactly, great, indeed. So we have this negation here. So as was said, this becomes false. So we get true and false. And if we check our little table here, true and false becomes false. They both need to be true. Yes, perfect. Okay. So that is indeed our first one. So if we have not A implies B, what do we get? I see it true. Anyone else in the chat? True. Yes. Okay. So that is indeed the case. So what do? We put A is true in there, but because of the negation, it becomes false. And B value is true. So we do false implies true. We check our table again. Remember implication. I didn't study, but I still passed. Hey, that is great. So it is true indeed. Like that. Okay, and for our last one, we have A or B or C. So what do we get? True, exactly. We just need at least one of them to be true, right? And we have both A and B are true here. So then indeed we will have our value of true. Okay, let's try our hand at ones that are a bit bigger. So let's say A is true, B is true, C is false, and D is true. For this first one, what would you say? So maybe Max, do you know? How would we go about this question? Or anyone else in the chat?
So I think we can start by kind of doing both of these things in brackets and just figuring what they are before we move on like to the whole implication.
Mm-hmm.
We have A, which is true, and not C. So we have true. And the second one, we have not D, so we have false or not B, so false.
Mm-hmm.
So we have that true implies false, and that's false.
Yes, exactly. Great. So indeed, as was asked in the chat, we should separate the equation to make them easier, and that's exactly what you did. So that is good. You just fill in the equations one by one, and then we go further. So could you also try the second one?
Yeah, sure. So we have A, which is true, and B, which is also true, and not C, so that also makes it true. So we have true, 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 which is true. And then we have not D, which is false, and not C, which is true. So that second bracket kind of yields true because it's or. So we have that true implies true, which is true.
Yes, great. Exactly. Thank you very much. That was great. Maybe Roberto, do you want to try the last one?
So we have A, which is true.
Mm-hmm.
That implies not D, which is false.
Yes.
And then we have goes to C, which C is false.
Mm-hmm.
And that holds up. So it's true.
Yes, so we get false, right, on the left-hand side, because it's an and sign. And sorry, that is indeed true, because I did not study and I did not pass, so that makes sense. So that is true, indeed. So that is how you would go about logic. So in order to make this even more easy for you, we can actually make use of something called the truth table. So the way you use this is you define the variables that you have. So in our case, we have A, B, and C. And you want to know for every single, so these are just, we only know for A is true, for B is true, for C is false, for D is true, right? And it takes quite a while to write every single combination down. So in order to know it for this formula, for example, we can make a truth table. So in order to write down the correct combinations, you can have A is true 4 times and 4 times. So you switch from true to false 4 times. Here you switch every 2. And here you switch for every one of them. So if you do this, then you know for sure you have all possible combinations. And in order to know how many columns you need how many rows you need in total, you take 2 to the power of n, where n is the amount of variables you have. So in our case, we have 3. So 2 to the power of 3 is 8, right? So we know that in total, we need 8 values here. Same for if we would only have A and B, then we would have 2 to the power of 2, we would have 4. Right? Remember with P and Q, we have 2. So then we only need 4 rows here. So that's a little trick to remember. 2 to the power of n gives you the amount of rows you need in the truth table. Okay, so if we would solve this truth table, we have our values of A, B, and C. So we kind of apply the same thing as we did before. And we are indeed breaking up the formula such that we can then compare it to this column here. So if we have A and not B, could anyone tell me what values I would have to fill in here? Maybe Omer, could you tell me? So for A and not B? Okay, first one, false. Yes. And then if you would just fill the rest in. And then true for the next one. A and not B. Let's see. So we have the same values here for the second and first. So we have, oh, for the one on the right. Okay, yeah, let's just go down. Oh, okay, you're right. In that case, yes. But if we would go down, then this one would be false as well, right? And then what would we get after that? True, and then that one is the same, so also true, right? Oh. Then for this next one, what do we get? True as well, yes. Because we get, oh no, sorry. We get A, which is false and false. So that would be false, right? If we were back, false and false is false. So these two would both be false. I don't know what is happening to this pen, but okay. oh, I'm messing it up. I'm sorry. This pen is distracting me. Can I just, okay. So let's look again. This one was true, right? This one was true. This one was false, and this one was false. False implies false is true. Yes, that is correct. But now we are looking at a conjunction, not at an implication. So we're looking at the and symbol and not the implies symbol. Yes, okay, great. Then I hear false again. Yes, that is true. And then false again, right? Oh God, I really don't know what happened here. Oh my God. Okay, I'm so sorry. I'm just gonna write it down quickly. True and true. False. 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 Okay, I don't know what is happening to the pen. I'm gonna check that out later. Okay, but this is indeed the first column. And then for the second one, what do we get here? So you already just said we have to compare A to this column. So we have A, a value of true. I'm so sorry, guys. I'm gonna try and figure out what is wrong with the pen afterwards. But if we would write down the rest of the table, what do we get? You get true, A, and for this first one, we get true and false, right? So is that true or false? Remember, for and, we need both of them. So, oh yeah, sorry, I'm looking at the implication. Yes, you're right. Oh my God, the pen is not working anymore. Okay, so we look at false implies false. It's true. Yes, sorry. So you're right. That is true. For the next one, we have false implies true. Which is true. Yes. Then we have true implies false. False, great. Yes. Then we have true implies true. Yes. Then we have false implies false, which is true. Yes, exactly. So if we fill in the rest, we get, let's see, false implies true, which is true. We get false implies false, which you said before is true. And the last one, we get false implies true, which is true. Yes, okay. So we've reached 12:30, so let's stop here. And then on Sunday, we will continue with satisfiability, validness, models, entailment, DPLL, and clause normal form for logic. And we will also go through set theory again. And then we will make the exam questions or extra practice if we have time left as well. So that is it for today. I will send you the slides. And are there any final questions for today? And you can always also ask any questions in the chat you have in the group chat. So if there are no questions left, I'm really going to check out what is happening to the pen because this is really annoying. Okay. So then can we have the exam before? What do you mean? Like if I can give you the exam? Yeah, no, I cannot do that. I'm sorry. I also do not have access to the exam questions. So I cannot send you it. But also I wouldn't because I'm a TA and that is not allowed. All right. So if you don't have any questions, I'll see you tomorrow. So thank you all for your participation. And let's see each other tomorrow again at the same time. All right.
Hi. I have
Hi.
a question.
Yeah, sure.
So if I have already done the course before and I passed the assignments, I can skip them this year, right?
I believe so, yes. But I think you would have to contact the professor to let them know so they can like take your grades from last year from the exam, from the assignment, sorry, and then transfer them to this one.
Yeah, this is why I wanted to ask you because on the Canvas page it says to ask the teacher on the last week, but I'm not sure if that's true, and I'm scared to be like too late. Yeah.
Oh, I would just send him an email right now.